A recirculator is a vessel designed to supply liquid refrigerant to the evaporators at a controlled rate while collecting and returning excess liquid refrigerant for reuse. It is primarily used in large industrial refrigeration systems, particularly those using ammonia as the refrigerant. The recirculator provides efficient refrigerant distribution, ensures the entire evaporator tube surface is wetted, and allows the system to use less refrigerant than gravity-fed or flooded systems. A recirculator is typically part of a package consisting of a large recirculator vessel, an oil pot, and one or more pumps. Recirculators can be designed for horizontal or vertical orientation. Most often, the recirculator receives liquid from a high-pressure receiver. Before entering the vessel, the liquid passes through an expansion device that lowers its temperature and pressure. It then supplies, by gravity, low-pressure liquid to the ammonia pumps mounted underneath the vessel. Liquid and vapor returned from the evaporators are separated inside the recirculator to allow only vapor to be piped to the suction inlet on the compressor.
All right, here I'm standing in front of a high temperature recirculator. I'm actually at a facility that has two recirculators, one high temp and one low temp. Next to that, a vertical high pressure receiver, but we'll give an overview of this high temp recirculator to give an idea of how these are configured. So follow me, let's look behind the vessel. So high pressure liquid from the high pressure receiver is piped through this valve groove that goes through an isolation strainer solenoid, and then this is a motorized expansion valve where it lowers the temperature and pressure of the liquid as it enters the vessel. Okay, this valve, both the motorized expansion valve and the solenoid valve, are controlled by the level probe, which is on top of this level column. So at the top of the level column, there's a probe going all the way through that that's interlocked with those valves to precisely control the level in this vessel. From this vessel now, liquid obviously comes to the bottom, vapor to the top, which is supplied back to the compressors. It feeds these pumps, and there's two pumps. They're insulated, so you can't see the pumps super well, but these are hermetically sealed pumps. So there's less leak potential, there's no shaft seal where it can leak. Liquid is supplied to these pumps and then pumped out through this pipe, which they share, out to the evaporators, which are up on the roof. All right. There's two pumps, and that's simply for redundancy, not because the two would run simultaneously. If one pump fails, the other will turn on. They can alternate back and forth, lead and lag. So our high temp recirc liquid line pumps to the evaporators, and then wet suction, which is called high temp recirc suction, is piped back to the recirculator, where any liquid droplets fall to the bottom are resupplied to the pump. Vapor goes to the top and is fed to the high stage compressors. If you follow me this way, I'll point out a couple more things about the recirculator. You'll almost always see an oil pot on a recirculator. It'll be installed at the low point. The oil is heavier than the ammonia, drops to the bottom and is allowed to drain into the pot. And you can track the oil level by looking at the frost line on that pot and know when oil needs to be drained.
Recirculators are often configured with a level probe that is interlocked with an electronic expansion valve to precisely control the level in the vessel. Because recirculators also provide vapor to compressors, they must also be configured with a high liquid level cutout that is wired to de-energize any compressor that receives vapor from the vessel. If the level drops too low in a recirculator, it can cause cavitation at the pump inlet, which is undesirable. Cavitation is a phenomenon that occurs when the pressure of a liquid drops below its vapor pressure, causing the liquid to form vapor bubbles. These bubbles collapse violently when they move into higher pressure zones, leading to damage, noise, and reduced efficiency in refrigeration pumps. To protect against this, the recirculator will also have a low level or cavitation cutout.
Let's contrast a float tree setup to a level probe setup on a recirculator. All right, so we're looking at two recirculators here. I haven't shown the pumps, you can imagine those, but we've got two vessels. They're pretty much configured the same. We'll say they're the same size, diameter, length, but the primary difference is in the method of level control. In the first here on the left, we have what I'm calling a float tree. It's equipped with 3 float switches. Typically, these would be like a ball float switch, and they're each interlocked with this recirculator to perform a function. All right. It may be that this middle one would be most commonly interlocked with a solenoid valve to control the level inside the vessel. We might call that an operating level float switch. That's what that one is. The one above it is our high level float switch. Remember, we don't want there to be any liquid in our dry suction into the compressor. So if the level gets too high, we want to trip those compressors so they can't operate and get slugged with liquid. That's the high level float switch. And then the bottom one, maybe to protect the pumps. If the level gets too low for some reason, we want to protect the pumps from cavitation. We might have a low level cutout. Okay, you could have even more cutouts, more float switches, more cutouts. Let's say there was a liquid transfer system, but this is providing that example. Historically, this is widely how recirculators were set up. On a more modern recirculator, it's more common to see a setup similar to this now. Notice I've replaced the hand expansion valve that we had now with a motorized expansion valve, so we're a bit more sophisticated. And instead of the float tree, we now have a level probe. There is a float, and we'll talk about that. But this level probe now provides continuous level monitoring and interlock capabilities. So we're able to more precisely control our level based on a specific percentage instead of just at fixed intervals like you have with a float tree. So that provides more precise control of your recirculator level. And this probe provides you with your operating level, your low level, and your high level all in one component. So what's the float switch for? Well, really that becomes a backup at this point. It's still a high level float switch, exact same function as we had on the float tree. And we do that simply as a backup. If this probe fails, we still want to protect those compressors, make sure they don't get slugged with liquid.
Most often, a recirculator will be equipped with 2 pumps to provide redundancy if one pump fails. Historically, open drive pumps were used. These pumps use a shaft seal that requires lubrication and is prone to minor leaks. To address this, it is now more common to see hermetically sealed pumps used in a system design. A hermetically sealed pump is often called a canned motor pump because the pump and motor are enclosed in a single sealed housing, which eliminates the risk of refrigerant leakage.
2 categories of pumps to be familiar with are the open drive and hermetically sealed pumps. Historically, the open drive pumps were what was available, widely used, often for ammonia system manufactured by a company called Cornell. And these were reliable machines, but unfortunately, the downside was they had a shaft seal to seal the motor shaft to the pump shaft. And that seal required lubrication through oil, and if not installed correctly or maintained properly, they were subject to leaks. However, I do want to say if maintained properly, installed correctly, these can operate very, very well for a long period of time and were widely used with success for many years. However, more recently, especially in the last decade, they've by and large been replaced by what's called hermetically sealed pumps. More candidly, sometimes they're called a canned motor pump, and that's because the pump and the motor are canned together in a single enclosure, so we have no more shaft seal. And that's a big advantage because it reduces that leak potential. So all other things being equal, a hermetically sealed pump is an advantage over an open drive pump just because you reduce the likelihood of a release. Performance-wise, both can provide overfed liquid from a recirculator, or transfer liquid throughout a system. So both work, but that just provides the overview of 2 different categories.
A recirculator pump will typically supply more liquid than will boil in the evaporators. When this is the case, the evaporators are said to be overfed, and this method of supplying evaporators is rightly called pumped overfeed. The ratio of the liquid fed by the pump to the amount of vapor formed in the evaporators is referred to as the recirculation ratio. If a pump can move 30 pounds per minute but only 10 pounds per minute of vapor is formed, the recirculation ratio is 30 divided by 10, or 3 to 1.